When the $10 billion device trained its infrared vision on the exoplanet K2 billion, 120 light-years away, it detected dimethyl sulfide, a sulfur compound that, on Earth, is produced exclusively by organisms. Does this mean the matter is settled? Can we finally answer the oldest question of mankind, whether we are really alone in the universe, with a clear no? Well, that is precisely the crux of the astronomical debate. While one side of the experts is already popping the champagne corks, the other side is calling for a little more patience and pointing out that even the capabilities of the most powerful space telescope of all time are limited. Hand on heart, in most people's daily lives, dimethyl sulfide, or DMS for short, probably plays no significant role. In fact, most people have probably never even heard of this particular chemical compound, even though they have very likely encountered it at one time or another. In detail, DMS is formed by microscopic algae, the phytoplankton, which drift in the uppermost layers of the ocean, and it is responsible for the typical smell that we notice when we are at the beach. Apart from its sniffing properties, DMS also has another important characteristic. So far, we only know of biological sources for this sulfur compound, and where the production of a substance requires the help of organisms. It is understandable that DMS plays a very special role in the search for extraterrestrial life. This makes even more understandable the cries of joy that came from the lips of Cambridge astronomers in September 2023. After all, the James Webb telescope had detected nothing less than this potential biosignature on the exoplanet K2 billion. The overwhelmed discoverer Niku Madhusudan then told the press that he and his colleagues were completely shocked by their readings. No wonder, because after all, the existence of DMS in the vastness of space is nothing less than a serious indication of extraterrestrial life. What initially came as a shock to the experts soon developed into almost euphoric reporting, which unceremoniously elevated the James Webb telescope to the key to the cosmic search for life. The overwhelmed discoverer, Niku Madhusudan, then told the press that he and his colleagues were completely shocked by their readings. No wonder, because after all, the existence of DMS in the vastness of space is nothing less than a serious indication of extraterrestrial life. What initially came as a shock to the experts soon developed into almost euphoric reporting, which unceremoniously elevated the James Webb telescope to the key to the cosmic search for life. But is the matter really as clear-cut as it seems? If the corresponding molecule on Earth is only produced by living things, and we then discover it on an alien body, why hasn't NASA officially announced that our microscopic neighbors are slumbering on K2 billion? Well, that's because, as so often, the devil is in the details. But basically, the conditions in the case of K2 billion are anything but bad. The water world, located about 120 light-years from us in the constellation Leo, is under the exciting suspicion of being a Haitian planet. In other words, a planet whose surface is completely covered with water and can therefore support life. And while K2 billion was added to the star charts in 2015 with the help of the Kepler Space Telescope, it orbits its central star, the red dwarf K2 within the habitable zone. This, in turn, describes the distance range at which a planet must be located in relation to its host star for water to be able to exist there in a permanently liquid form. As we all know, the cool, wet element is considered one of the fundamental pillars for the development of life similar to that on Earth. Although K2 is significantly cooler than the Sun, its planetary companion receives roughly the same radiation as our Earth due to the given constellation. The bottom line is that K2 billion is only 0.14 astronomical units away from its parent star, so it takes just 33 days for a complete orbit. Indeed, the pro column on this live discussion list also contains the entries methane and carbon dioxide, thus two further indicators that suggest we may actually be dealing with a habitable planet here. If this is really the case, it would be a cosmic novelty because, so far, these exotic water worlds only exist on paper. However, while the detected large amounts of methane and carbon dioxide, in combination with the lack of ammonia, suggest that K2 billion is a Neptune-like planet covered by liquid water, the detected substances also present an unfortunate complication. They make it all the more difficult to interpret the DMS data correctly. The mystery of the biosignature, in principle, is that the DMS signal was anything but pronounced in the collected data sets, and it only revealed itself when the data was analyzed in a very specific way. The matter was not made any less complicated by the fact that the DMS signature identified by Webb's near-infrared spectrometer NIRSPEC appeared in a spectral line at a wavelength of 3.4 micrometers, and thus in the very range that overlapped with methane. That is precisely the crux of the matter, because the scientists believe distinguishing between DMS and methane is simply beyond the capabilities of NIRSPEC. But does this also mean that Webb's capabilities have already been fully exhausted and that we will not be able to uncover the true background to the DMS question? Well, fortunately not. The researchers also emphasize that unequivocal proof is possible in principle. After all, DMS and its breakdown products also generate a signature in the mid-infrared range between 9 and 13 micrometer wavelengths, and conveniently, this is exactly the range in which Webb's mid-infrared instrument MIRI works. While the first NASA announcements still spoke of a possible detection of the molecule dimethyl sulfide in this context, the Cambridge scientists finally wanted to know more. And so it happened that the astronomers once again used Webb's sharp infrared vision to get to the bottom of the mystery surrounding the supposed biosignature. In the course of this, the experts allowed 8 hours for the targeted search for DMS. 1 to 2 days later, the research team. The process should begin with receiving the data and initiating its evaluation. However, as is often the case with such significant scientific endeavors, this type of data evaluation is inherently a labor-intensive and time-consuming task. In other words, it can take months, if not longer, before the entire evaluation is fully completed and the results are ready to be shared. Despite this challenge, there is encouraging news. The experts involved in this project have already been working on the analysis for over 6 months. This progress suggests that it may not take much longer before the latest findings regarding the potential presence of DMS dimethyl sulfide on K2-18 billion are finally published. When it becomes possible to detect DMS, it is fortunate that the wider astronomical community is not relegated to simply waiting passively for these results to emerge. On the contrary, they are actively pursuing alternative approaches to address the question of DMS detection. Specifically, scientists are exploring the matter from a theoretical standpoint. By leveraging sophisticated models, researchers can estimate when it might become feasible to detect the existence of DMS on K2-18 billion. One notable example of this effort is the work led by Shang Minai and their team at the University of California, Riverside. This research team has undertaken the ambitious task of reconstructing K2-18 billion and hypothesizing about its possible biochemistry. To achieve this, they employed various models simulating both the planet's oceanic and atmospheric environments. The simulations allowed them to explore several critical aspects, including the amount of DMS that hypothetical extraterrestrial microorganisms on K2-18 billion would need to produce for it to accumulate in the atmosphere at detectable levels. They also investigated how quickly such DMS might be broken down by radiation, a natural process that significantly impacts the compound's persistence in an atmosphere. The study concluded with an exciting and optimistic outcome. The ongoing data evaluation efforts by other research teams are not in vain. Theoretically, it is possible for biogenic sulfur gases, like DMS, to accumulate to detectable concentrations on hydrogen-rich ocean worlds, such as K2-18 billion. However, as is often the case in science, there is a caveat to this promising scenario. This optimistic result hinges on the assumption that the microorganisms on K2-18 billion are exceptionally productive. In fact, the level of DMS production by these extraterrestrial life forms would need to exceed that of Earth-based organisms by a factor of 20 for us to detect it with current instruments. This requirement stems from a crucial limiting factor. Most of the DMS released into the atmosphere would be rapidly broken down by photochemical processes driven by solar radiation. Interestingly, the study also proposed that in cases where DMS concentrations reach significantly higher levels plausible for hypothetical ocean worlds, another phenomenon could occur. The degradation products of DMS, such as dimethyl sulfide and methane ethyl, could form a natural protective shield in the planet's lower atmosphere. This shield would effectively slow down the rate of DMS breakdown, potentially enabling its accumulation to detectable levels. Despite these promising findings, the extent to which this theoretical scenario aligns with reality remains uncertain and will only be confirmed through future investigations. Nevertheless, one fact is already clear: a definitive confirmation of DMS on K2-18 billion would represent an unprecedented milestone in the history of space exploration. Such a discovery would not only highlight the potential for life beyond Earth, but also revolutionize our understanding of biochemistry in extraterrestrial environments. Currently, a team at Cambridge is diligently working on analyzing new datasets to further clarify the possibility of detecting DMS on K2-18 billion. The lead scientist emphasizes the profound implications of even a single confirmed detection. Such an event would have the power to transform the entire trajectory of science. After all, humanity has pondered for millennia whether life exists beyond Earth. It would only take one verified example to definitively answer this age-old question, instantly ending centuries of speculation and ushering in a new era of exploration. Although it remains uncertain whether the breakthrough in the search for extraterrestrial life will be attributed to K2-18 billion, no other known candidate currently offers such a promising lead. The trail of discovery continues to build momentum, and the scientific community is eagerly awaiting what the future holds. Meanwhile, the conversation about K2-18 billion serves as a reminder of the profound possibilities that await us in our quest to understand the universe.